Hi everyone. I am doing a little overview of the lesson that we did uh, on Thursday, April the 15th, because I forgot to record and want to make sure I give you a little overview about what we did today. I'll be uploading this recording into this slide once it's done. But we started off with a quick check-in question about what was their favorite method of laughing, and it was great. A lot of the students, or a lot of us, had said that the best laugh was those horrible out of breath laughs that hurt your stomach, but then the pain is worth it. We moved on to our agenda. So we were hitting Riemann sums and sigma connection, the integral symbol, which looks something like this, and the checkout, and then the fact that the next async was due Friday, which I'll perhaps extend to Monday because we kind of want to talk a little bit more about it. So that's what we did today. So let's jump into it. We had a little bit of a recap. So in our recap, we talked about the fact that we did a notice and wonder about the different kinds of Riemann sums, as well as their sigma notation representation. Um, I mentioned that a lot of us thought that the left Riemann sum underestimated the area, the right Riemann sum overestimated. A lot of you had believed that the midpoint was a really, really good one because it's kind of in between the two. Nextly, I'm recapping that the other day we did a left Riemann sum. We used the function itself to calculate the heights of the rectangles, and we multiplied with the base of the rectangles to get a total area of 6.75. So we did that the other day, and we had a little bit of practice. After that, we moved on to reviewing how to use sigma notation. For example, the fact that sigma notation is a condensed way to represent an expanded sum. And why is that important? Because when we're doing a lot of rectangle calculations, what we're doing is we're doing a lot of sums. And so sigma notation is going to come in as a condensed way to represent those sums. The essential question that I had you all think about is, how is sigma notation connected to Riemann sums? We paused here and had you all think about this essential question that we're going to investigate today. And then back to this. So we're going to go ahead and focus on these these representations for the visual of finding the left, right, or midpoint Riemann sums. But I expressed that we're going to only take a look at the left Riemann sum, and that if you want to, as a student, explore the right and the midpoint connections, you are free to do so. Those might show up in the AP exam. But for the sake of hitting our essential question understanding, we're going to focus on the left Riemann sum. Okay, so we started off with re-engaging with what we did on Tuesday, which is we did a left Riemann sum to approximate the area under the curve of our function f of x equals x squared between 1 and 3. So I mentioned that in order to make the connection, we're going to find the patterns that are happening. So I noticed that to get the function heights, there is a pattern. It's the fact that I am taking a subscript input. So for example, as I'm plugging in whatever x sub 0 is into my function to get the output, I'm plugging in whatever x sub 1 is right here, the upper left-hand corner, to get my output, and then so forth. So essentially, the formula breaks down into this. We are finding the rectangle's heights by plugging in f of x sub I. This is representing all of those rectangle heights that you see right here. Because x sub I, the subscript I, is going to represent 0, 1, 2, or 3. So that is a condensed way to represent those heights. Another pattern that we pointed out was the fact that these 0.5s were always being multiplied to our rectangular heights. And those 0.5s, let me draw some arrows to them. Those 0.5s in calculus and in math in general, we call them as delta x, which means change in x. So we have our rectangle heights, we have our rectangle widths. We know that to find the area, to find the area of a rectangle, we multiply these two together to get the area, right? But not only that, we had to add up all of these rectangles to get the area, and that's where sigma's coming in. And we start at 0 because our first subscript input was 0, and our last subscript input was x sub 3 right here. So that's the last upper left-hand corner. That will stop at 3. And then here goes our formula, which is base times height of the rectangle. This right here is a condensed way to represent all the work you see here. And I also simplified that. I simplified that to be everything else the same except for the fact I replaced the delta x with the 0.5 because that was the common width of all the rectangles in this particular problem. There is the connection. So we paused for questions, and there were some questions that came up. But other than that, we went ahead and we processed our understanding of this connection in a Padlet was what happened next. So let me clear my slide. So we went on a Padlet. Let me show you all the amazing thoughts y'all had. Whoops, I had it open. And it is loading. So we were on column 7, and I asked you, with your own understanding, how is a sigma notation for the left Riemann sum connected to the visual? So basically, how is this connected to this? And in general, the whole class had a very unified understanding of the connections. A lot of you mentioned the height of the rectangles, the subscript notation being connected with how we start and how we end. So take a look at the commonalities there. A lot of you mentioned it's just basically representing what's visually shown in their graph. It says there it's the same, but it's just condensed. And a lot of you are pointing out that 0 at the bottom is showing that it's a left Riemann sum that's deep. We got the starting and ending point, height and width is represented in the sum, and so forth. So as you can see there, we're having some connections, which is amazing. And a lot of you are perhaps bringing in the subscript notation, which is even nice, and so forth. So a lot of you are making those connections, and we're able to kind of answer that essential question: how is sigma notation related to sigma? How is sigma notation related to Riemann sums? A lot of you are making that connection. Amazing. So then we moved on from that, and we kind of did a whole class exploration with this tool. So this was me at the front, and you all were taking a look at me playing around with this tool. So we noticed that the fact that 4 rectangles doesn't really approximate the area under the curve between 1 and 3 of our function really well. It doesn't. So we played around with the number of rectangles under the curve. So when we said, okay, let's try, I think someone suggested 26. So we did 26 rectangles. Take a look. 26 is a pretty good estimate. There is less white space under the curve. And if you scroll down on the tool, you see the sigma representation. And it actually calculates the area for you. So it's saying that it's about 8.36. Then someone else suggested 27. So we did 27. 27 looks very similar to 26 visually, but 27 rectangles is eliminating more white space from under the curve. And then we continue with the trend. So let's try 100. If you look at 100, that looks pretty cool. Until you zoom in, though, you see the white spaces are still there. Then I was trying to put another number, but somehow it kind of like went very large. I forgot. I think I put 230 or something. And take a look. It almost looks like a solid fill-in of that area under the curve. Except you do, if you scroll it, if you keep zooming in, you're going to see white space. Ultimately, we even did 1,000. And take a look at the area estimate, about 8.66. If you round it, again, this looks fully filled in. And if you zoom in, it's going to be hard. Like, whoa, where's the white space? But eventually you'll see it. You'll see some white space right here. So we went ahead and from this investigation as a whole class, we jumped back into the Padlet on column number 8, and I asked, how many rectangles would you say that we need to get the perfect area? We were on the right track because we all chose large rectangle numbers to represent that sum. I highlighted that a few comments, the fact that the bigger the number, the less the white there will be. because that's going to lead us into our big idea. I also pointed out another one that says, I would say NA because there's always going to be space under. So how can we get the perfect area? So I really, really highlighted this comment. And then again, there's that comment again, less white space of an estimate. You'll get more correct if you use more rectangles. That actually is highlighting the idea, the fact that the more rectangles is indeed better approximation. What does that mean? Let's make some connections. So we're going to make connections to this integral symbol. So far, y'all have seen this integral symbol as meaning antiderivative, but we're going to now connect this symbol to area under curve. So that is actually the mind blow moment. So we have right here a left integral with its sigma notation representation. So we've seen this already. Now we're going to transition into the better estimate. The fact that the more rectangles equals better was what was made as the connection even in the Padlet, right? So I went ahead and rewrote the sigma representation of the left Riemann sum. But if we want as many rectangles as possible, guess what, y'all? We're going to bring back limits. Let us make sure that we have the limit or the number of amount of rectangles go to infinity. So we have more and more rectangles. So this top number n is going to infinity. And when we have this, guess what, y'all? And then there's a little written description of what I just said. When we have an infinite amount of rectangles, everyone, that is the integral. So it's wild, right? So there is a connection to integral and antiderivative, which we will continue to explore. But now we have made a connection with this symbol and area under curve. This is going to give us the perfect area under the curve because we use the limit. So that was huge. That is a huge, big idea. And we then, and I put seriously because that's huge. And then we jumped into an application of the problem. So let's say on your homework, you see this. Find the integral from 0 to 2 of this function x dx equals. So step one, I said, is you should graph this function on Desmos. How I inputted it was y equals x. And because we know that this symbol means find exact area under the curve, let's go ahead and find the exact area under the curve from 0 to 2. Oops, because that's what it's saying, from 0 to 2. And let me change my color. But from 0 to 2, the area under the curve, y'all, it's going to look like a familiar shape that you know. By the way, y'all notice how when we say area under the curve in math, we stop at the x-axis. We don't go below it, like when it's like this. So I'm just shading in this area. And when I shade it in this area, y'all recognize this as something familiar. It's a triangle, basically. So we are able to find the exact area under this curve using geometry, actually. So I'm going to go ahead and share with you the ideas that was expressed by our very own students. An idea was, what if we imagine or envision this being a very large square? To find the area of a square, I know that the length is 2, the height is 2, so I would just do 2 times 2, which is 4. But because this is a triangle, we divide it by 2. So that was the solution that was offered by a student. And basically, we're able to evaluate this integral, and we get 2. 2 is the area under the curve. Like, we don't have any units for this problem, so we just write 2. So that is how we went through this lesson, everyone. Sorry for not recording. I hope you find this helpful. Yep.